So I'll introduce Gordon. So Gordon Cowell is another one of our specialist mesothelioma radiologists in the National NDT. Gordon has also been fairly active in our imaging research programme and more of the MR work, and so Gordon's going to give us a look to the future maybe and a bit more MR and those sorts of things.
Yep, absolutely. Thank you very much. I'm delighted to be here. You can all relax because there's still pretty pictures in this talk, but there's no audience participation, so I take that as an advance. So 3 broad topics today. First of all, we're going to have a look at how we're measuring response rather than initial staging. We're going to chat about MR and how we can use that and how it differs over some of the modalities, and a little taster on some of the current imaging research that's going on, and particularly in AI. So first of all, response criteria, which are called modified RECIST 1.1. So how are we using them? So why is accurate staging important and response important? Well, we need to give patients and clinicians really accurate information about, first of all, what is the basis of the patient's disease and how well they're responding to the patient, whatever treatment they're getting. We can see there that the staging gives really good information about patient survival. And it's a cornerstone of entry to surgical trials like MARS-2 or multiple oncological trials. So it has to be robust, it has to be reproducible, and it has to be usable. So it's a very catchy title, RECIST 1.1. So RECIST is a kind of worldwide system for describing tumours and creating a way that we can monitor them across a time period using different scans. Because mesothelioma is such a unique tumour with its kind of rind-like growth pattern in the lung, there's a completely separate set of criteria. And it basically makes lots of measurements in 3 key areas. First of all, it takes some pleural measurements. It measures any lymph nodes that are around about, and we'll look at pictures of them shortly, and also makes measurements of any disease that's spread further than that, any extrathoracic disease. So it started off in 2004, and you often think about these publications being validated in vast amounts of data, touching what Simon was saying earlier on about kind of surgical data. In actual fact, if you look at the first version of this, it was only validated in 74 patients, so tiny numbers. And these criteria have to evolve, and that's driven because our imaging technology is improving. It's because the treatment options are improving, so that demands high quality follow-up and also kind of research innovation as well. So if you look at that diagram on the left-hand side there, if you've got a spherical tumour like a lung cancer, it's very easy for me as a radiologist to describe that. It's 10 millimetres wide, it's round, it's well defined. You look at the image on the right, and that's a 10 millimetre wide rind mesothelioma, but it's potentially a much more complex shape. It's clearly a bigger volume, but how do I go about describing that accurately? And that's what gives us unique challenges for disease monitoring in mesothelioma. The other problem we've got, and we touched on this with the MDT, is that these MRECIST criteria diverge quite significantly from how people do RECIST. So radiologists who do RECIST probably do very little MRECIST at all, so it's a learning curve with that. And the other big difference between RECIST is we've got a default minimum sort of response measure of 2 millimetres, tiny amounts of disease, which is different from RECIST, so familiarity is a big issue. And another clear sign it's contentious is that as soon as the most recent imaging guidelines were published in 2018, there was an editorial detailing 4 areas that they disagreed with. So clearly lots of disagreement. So what does that break down into? Well, the first bit is the pleural measurements, and that's 6 transverse pleural measurements, so measuring at right angles to the pleura on 3 separate tumour slices that you can work out where they are in future scans. And sort of take into account it being easy to measure, they've got to say disease has to be at least 7 millimetres thick. So really not very much at all. You think about how thick 7 millimetres is. You can see in this example here that this is disease all the way around here in each of these 3 slices. This is pretty thick disease. This is a radiologist, this is pretty easy to measure. But even then, there's issues with it. You might think, well, that's quite straightforward. In actual fact, even measuring this transverse is open to significant variability between different observers. And research has shown that you've got a difference of over 10 degrees in angles of measurement. Now, if you're measuring, a 10 millimetre tumour and measuring at 11 or 9 millimetres, that's immediately a 10% error rate. And we know from research there's actually about a 30% variation between different radiologists and different reporters. And what's even more, if you compare RECIST, where it's well used, lots of research, with MRECIST, we know that MRECIST were making judgments on whether tumours are getting better or getting worse based on much smaller changes in tumour volume, and that's a big issue going forward. So this is one of the issues. So this is a patient much earlier stage, much slimmer tumour, and you can see I've highlighted areas here. This is actually an example where I'd really hunt to look for 6 separate bits where we could reach that 7mm threshold. So an example where it takes longer, it's more time consuming, you've got to put a lot more thought into it. Luckily, the nodal disease and extrapleural disease is a lot more straightforward. So we can see here, this is a lymph node. So we all have lymph nodes, they're normal, but when they become enlarged with involvement with tumour, they're an issue. And this one's certainly enlarged, and that's pretty straightforward. That's the same as lung cancer. We're measuring what's called the short axis dimension, the kind of narrowest point of that lymph node. And then we're also measuring any disease out with the chest cavity. So this patient has got a couple of liver metastases, so spread of tumour into the liver here, and they're pretty straightforward to measure. And what you do is you simply add all those measurements together and get a sum, and you can compare that sum at different CT scans the patients get. But even then, there's difficulties. You know, this patient here has got a mental disease. There's no sort of fixed mass there. How do we measure that? Well, we can't really. There's nothing physical to measure there. We can simply say, is it present and is it getting better or worse? So once you've got that measurement, you can then calculate any change in measurements, change in the calculations. So very simply, if that calculation gets more than 20%, it's progressive disease, the patient's getting worse. If it reduces by 30% or more, it's getting better, so that's a partial response, and any figure in between those two is stable disease. So I've detailed some problems there. You think, well, that's fine, we're absolutely sorted. Well, in actual fact, even amongst people who do this regularly, there's disagreement. So as part of the study, the PRISM study locally, we had access to 266 tumour blocks and CT scans. And after applying some exclusion criteria, we looked at about over 172 patients who underwent CT before and after treatment. And what this found was quite concerning. So 2 radiologists, both involved with the Scottish National Mesothelioma meeting, one of whom was me, so I can shoulder some of the blame for this. In actual fact, 65% of the time we agreed. That's actually really pretty low. And when you start looking at a third of patients that were discordant, around 10 of those patients, we actually were completely different. So one person said the patient was getting better, and one patient said the patient was getting worse. And then we've got a group of around 50 or 30% in the middle where there's we're just sort of a couple of response criteria out. So for the stat boards out there, that gives a kind of moderate interrelator viability. So this is not what you want from a robust way to measure treatment response, and wouldn't really be acceptable, I think, in a lot of other clinical trials. So what are the causes of this? So when you dial down to it, on the left-hand side, we've got the 10 patients with markedly diverging issues. And what you find there is human error is the big issue. And unfortunately, these are things that just happen in real life. The wrong scan gets looked at, time points get muddled around, the criteria get incorrectly applied, maybe in an area of contention. When we look at patients where maybe there's smaller differences, you see maybe one person responded versus stable disease or stable disease versus progressive disease, actually it completely changes. The human error rate really reduces, and the vast majority of these errors become attributable simply to the design of the criteria, the MRECIST criteria themselves. Either because you've simply got very subtle disease differences in the CT scan that are difficult to quantify, or you've simply got less than 10% difference in measurements between observers, and that just crosses your threshold for the different criteria. So we've got real challenge with that going forward, and we'll touch on this later on. So we're going to move on to the kind of middle third now. So what are the advantages of using MR? So Simon's given us a great overview of CT and how we use CT. It's the real workhorse. It does a huge extent of the work that we do. But why might you want to use MR? Well, the great advantage of MR is there's not any ionising radiation. It gives us better contrast of soft tissues. And what I mean by that is we're better able to differentiate between different types of tissue in the body. So muscle, fat, lung, we can tell more easily. And also gives us what's called functional information. So actually what the body's doing on a kind of more microscopic level. So it's an incredibly useful technique. It's also really time consuming. You can fire somebody through a scanner, the scan will literally take a second or two. An MR scanner, for pleural MR, probably you're going to be on the table for a good half an hour, 35 minutes, depending on your scanner. It's a lot more expensive, both in terms of your initial capital outlay. You know, a decent clinical MR scanner is not going to leave you a huge amount of change out of £1 million. And the access is a lot more limited, partly for that reason, the NHS, financially, and also you need slightly more experienced staffing as well. So we've come a long way. So the image on the left is a guy called Raymond Damadian, and he was an American physician. He was the first person to actually use MR to diagnose tumour in a whole body MR scan. And the image on the left is a kind of seminal paper from the kind of Nottingham group led by Peter Mansfield, and he basically showed some abdominal images. So we have come a very long way since then, I'm pleased to say. It is a real triumph of kind of medical physics, I think. So how do you go about building an MR protocol that is going to diagnose pleural cancer? So a lot of people get really scared of MR because there's all these different sequences, it looks different. In actual fact, the building blocks of a kind of high quality pleural MR protocol are actually pretty standard. They're pretty ubiquitous to a lot of different imaging. And there's probably 4 different strands to it which we're going to deal with. So the localized images are simply sort of lower quality images that we use to plan out the study. And we're going to go through each of these 3 separate types of imaging in turn. So people sometimes say, well, how does an MR scanner work? Well, one of my now retired colleagues, Ian Robertson, wrote a book, and he came up with a great quote that said, MR is best considered as a magic box that gives beautiful images. It's probably a little bit simplistic for radiologists, but I think to those intents and purposes, it's probably a good way to look at it. Basically what happens is there's a very strong magnetic field, a radio frequency pulse is applied to the patient, and we're able to measure the responses we get from that. And depending on the pulse applied, we kind of emphasise different aspects of the body. So T1 weighted imaging is one of the kind of cornerstones, and it really emphasises the fat content of the body. And this is what we use a lot for pleural imaging. So this is a patient who has had an initial scan, so it's coronal, so remember looking face on to the patient, and they've been given contrast. And that's why all of a sudden these areas look much brighter. That's because your contrast dye has been injected in through a vein, probably in your arm. And you can see over time, initially it's very bright, and there's gradually dips in brightness as it gets spread around the body, and also gradually it just gets excreted out by your kidneys. So what information can we tell from this? Well, Selina came just a paper a few years ago that looked at this really nicely, and you can see here this is an example from that paper of a patient with concentric tumour, MR showing it really beautifully. And what she described was a phenomenon called early contrast enhancement, where we see a more rapid increase in brightness of that tumour because it's taking up more of the contrast, and then it levels off. If you look here, this is a graph of somebody with BAPE that Mark mentioned earlier on, where it's benign disease, and we've got a much flatter, slower increase in that sort of contrast uptake. So that we can quite safely say is benign. So that's how we use the T1s. And these are the timings we do. So we give contrast and we do scans at these time points. These are relatively arbitrary. The first couple are pretty important for all scans. After that, you can probably tinker around with them quite a bit depending on what your scanner type is. So T2 weighted imaging, the T1 emphasises fat, whereas T2 imaging is both fat and water. And this is probably better for looking at your lymph nodes, looking at things like your pleural effusions, so is there any complexity to it, are there lots of pockets to it, and looking for some incidental findings as well. Does the patient have something that you're not really expecting? Diffusion weighted imaging. So diffusion weighted imaging is based on a principle, it's called the random Brownian movement of water molecules, and very simply that means that in your body the water molecules can kind of move around however they want, and it's random and there's not really any pattern to it. But what we know is that tumour or types of tissue that have very densely packed, lots of cells in them, like cancers, like tumours, or areas of dead tissue, for example, if you have a stroke in your brain, the water molecules can't move around as much, and that's when we talk about restricted diffusion. So it's really, really useful in characterising tumours and strokes as well. So how do we use this in practice? Well, diffusion images look a bit weird. They're functional images, so they're describing a bit of the body and the way it works rather than giving us an anatomical depiction of what's going on. And we can see here these lots of little white dots all scattered around the pleura. And these are areas where those water molecules can't move properly, of restricted diffusion, and we can confidently say that's tumour. So why have I got a picture of our self-portrait of Vincent van Gogh? Well, this is because this term has been called pleural pointillism. So the art buffs amongst you might know that pointillism is a technique where you make lots of dabs with your paint. And the authors of this paper thought that looked very similar with these little studs of brightness on the pleura and the MR. So I'm going to bring a little bit of culture to your afternoon. So I occasionally chat to people or chat to radiology colleagues and they say, well, this is all very well, doing this lovely MR protocol. We don't have access to a 3T, research MR scanner. You're spoiled. Well, in actual fact, so these are the images we get from the 3T scanner in the clinical research facility at the QE. So 3 basically refers to the strength of the magnet. So 3 is a stronger magnet, and most clinical scanners are about half that, or 1.5 Tesla. And these are the images that we got actually just 2 or 3 weeks ago on our standard clinical scanner at the New Victoria, and actually they compare really pretty well. So if you've got a decent clinical scanner, there's no reason why you can't be doing this protocol yourselves. Okay, so we're going to move on to the kind of final third of our talk now, and we're going to chat a little bit about what the future might hold and how it might progress. So you can't really start any imaging talk these days without considering artificial intelligence. It is everywhere. If you go to the big European Conference of Radiology, which is in Vienna in March, everything is about AI. And there's a really famous quote that AI is not going to replace physicians, but it will. Physicians who use it will predominate. And in actual fact, that really is very much the same for radiologists. If we use AI, I think it will augment what we do. It will cut away those kind of repetitive tasks that take a while but don't necessarily need kind of high order thinking. So before we get too excited about what the radiologists of the future might hold, let's have a look at some of the kind of most recent literature on this. So obviously you've got an AI tool, and clearly you're going to use it to then see, can you pass the exams that radiologists have to sit to be a radiologist? So you can see here on the left-hand side, this is in the BMJ, it's a British article produced by Susan Shelmerdine, who's a paediatric radiologist down in London. And they looked at an aspect of our exam where you have to look at 30 X-rays in 30 minutes and decide whether they're normal or abnormal. And in real life, you need 90% of that, about 90% to pass. And they, quite scarily actually, came away with an overall accuracy of about 79.5%, which is pretty good. It's not good enough. And in actual fact, their model was only able to pass 2 out of 10 mock exams. So the Americans thought they'd try this as well, and they had a look at their MCQs that they need to sit as part of their board exams. In actual fact, they plugged this into G, and it managed to answer just over 2/3 of the questions correctly. Not surprisingly, it performed much better than things just required direct recall, lower order thinking, but they performed worse in questions that needed maybe a couple of stages of thinking or a bit of clinical application. So much to my eternal relief, AI is currently a fail, but I suspect that I'm not massively far off showing the same slide in a few years' time and saying a pass. So thinking more widely about radiology, how are we going to use artificial intelligence? Well, it is going to revolutionise every single aspect of how I work and how my department works. And you can apply it in a myriad of ways, not just in mesothelioma. So you can use it either to improve your image quality, or you can use it to maintain your image quality and reduce how long a scan's taking. So that would be really useful in mesothelioma, where you've got prolonged imaging times. You can, I mentioned ChatGPT earlier on, but you can use it to do things like construct reports, run sort of structured reports, highlight information that you might want to pull out for QPIs. You can use it to detect and classify abnormalities in imaging that we looked at in the previous. And some people say you can actually use it as a virtual assistant as well. You can sort of triage cases, suggest diagnoses, vet things. So it's going to revolutionise how we work. And all the strategies that we use from now on probably tie into this in various ways. So this is a paper that Andrew Kidd had produced under Kevin's supervision a couple of years ago. And one of the ways, instead of producing lots of measurements of transverse tumours to look at the volume of the tumour, can we use changes in volume of the tumour to measure how the patient is getting on when you give them whatever treatment you want to give them? There's problems with this. In CT, because you don't have that inherent differentiation to the soft tissues, it's hard on CT. And also there's lots of variabilities. the radiologist may or may not have had coffee. There's different acquisition parameters between the imaging. The patients might be different. They might take a different breath in, different software, huge amounts of variety. And on top of that, there's currently no guidelines for saying if we've got this amount of change in volume of the tumour, it corresponds to this degree of response. That doesn't exist really at the moment. So this paper looked at doing some ground truth for human annotations, then creating a deep learning model where AI would be able to segment out the tumour itself. And it did that pretty well, actually. It's really, really important to get this done because each of these annotations took Andrew, I think, over 2.5 hours. So this is well beyond the kind of the limitations of what a clinical radiologist could do in the timescale. You're quite a hard crowd because normally I say 2.5 hours and there's an audible gasp. Obviously, you're a hardened bunch. AI is not perfect, it's pretty good. I mean, so there's only about 4 out of the 60 validation cases that had errors. And we can see, for example, up here, that is tumour that's extending into a fissure in the lungs or between the lobes. The AI didn't pick up. To be perfectly honest, this is an example of somebody with lots of tumour and collapse of the lung at the base of the lung. I'll be perfectly honest, I don't actually know in that one who's closer to the truth, the human segmentation or the AI, because it's just really hard to tease that out, and that is where MR would really help. And in the final one here, we've actually got the other side, the left-hand side, was actually just normal, apart from having a small pleural effusion. It's picked up having a disease. So not perfect, but an awful lot better than having somebody sit there for 2.5 hours to look through each individual one of these. So another technique we're looking at is radiomics. Now, radiomics is a radiological technique that has taken off in radiology in the last few years. If you look at the graph of radiomics publications, on PubMed, it's exponential and it's still climbing. So I looked up a definition of radiomics, and this was from one of the radiology journals, and it's the really catchy mathematical extraction of the spatial distribution of signal intensities and pixel interrelationship of medical images, which is really, really clear. Actually, it just simply means ways to describe an image that features are too complex or too subtle for the human eye. And we've actually got a kind of work stream now on the left-hand side there that's really well established for radiomics. So why hasn't really much work been done on this in mesothelioma? It all comes down to one thing: image segmentation. If you're having to do this as a human at 2.5 hours before, projects like these, to get enough numbers to do it, would take literally months to years. It's not a feasible project, enough numbers. But if you can then use a machine learning model to accurately segment that for you, that becomes a very, very useful tool. We've done some work with Alice Bloom, who's an image analyst with the university, looking at some of these features. And we took some of the scans from the PRISM study that would been pre-segmented. And Al's used those to extract some of these radiomic features. So he looked at 68 separate features, and then looked at which of those didn't correlate with random noise. And any that did correlate with random noise obviously don't correlate with the tumour, so they just got binned. Out of those 47 features, 13 of those features really didn't have much correlation at all, and we extracted those to try and combine them to try and predict things. And actually, the model that Alf produced, he looked at 3 machine learning models, and the model he used actually was able to predict patients who get chemotherapy resistance with an accuracy of 93%. Now, that's really, really useful information, particularly if you're talking about if you've got options for kind of personalising treatment regimes. And you can see the image on the right-hand side. People love colour images in radiology, but this is a nice example here of differences in disease response. So the particular radiomic feature here is actually titled high grey level run emphasis. And all that means is the model has looked for strips of higher density tumour sort of running in straight lines in any direction. And what we see here on the left-hand side is that the patient who's progressed has got much, much lower global volumes than the patient who's had a partial response to the tumour on the right-hand side. So another way you can potentially categorise patients and potentially alter their treatment if you have that option in the future. I'm not going to go back through the meso-origins because Mark has done that very well already. And another area you can look at when you give a patient contrast dye in through their arm, look at how that contrast dye distributes into the tumour. So this is a group from the Balkans who looked at this a couple of years ago, and they showed really, really nicely that if you look at a variety of factors that you can draw out, that you can actually predict pretty well which patients are going to respond. So you can see here, they've measured what's called the area under the curve, and basically the higher the number, the better. And they've looked at this value, which is the K-trans, or your transfer constant, which is basically looking at how much your contrast moves from your bloodstream into tissues out with that, and how quickly it does it. And so it's kind of a measurement of how vascular something is on a very basic level. So that shows that pretty well. Now, looking at these images here, this is a patient with my mouse coming up. This is a patient with pretty extensive disease. There's really, really sort of thick disease. So can you do this on patients with much earlier disease? These are the patients, after all, that we were chatting about targeting earlier on. And this is work we've done locally that we're writing up just now for publication, that can you calculate similar parameters? And the answer is you can. You can do it by selecting these areas and calculating the kind of mean values. And what we found that is if you combine some of these factors with something like early contrast enhancement that from Selena's paper, that you can pretty confidently say, at the very least, that you've got a higher sensitivity and a good negative predictive value. So you've got a bit more confidence saying to somebody there's no evidence of tumour there. And this is work that could really accelerate if you have access to a machine learning model that automatically segments things for you. So just to kind of finish on, what I really love about MR is there is a vast majority or vast variety of different techniques in MR. I've plucked sort of 5 random things out of the air there. It could mean 5 different things, and all of these are worthy of exploration. And that's the thing I love about MR, so its flexibility and excitement for the future. So just to remind you, we've got standardised mesothelioma research scoring systems. They're entirely necessary, but they're currently pretty flawed. MR, a fantastic opportunity to combine both high quality anatomical information with some functional information, depending on what technique you use. And there is a pretty wide portfolio of research being done in imaging in mesothelioma, with both detection and monitoring disease in mind. And a reminder that artificial intelligence will completely transform every aspect of imaging. I'd welcome any comments you've got. It's a quid pro quo. I gave them no questions. They've got no questions for me.
Data is quite convincing that it's better than CT, but we're kind of stuck behind the kind of elephant in the room, which is that getting more MR scanners into that building and getting more MRI scans done and more radiologists comfortable with it is kind of almost a hurdle that seems like we just can't get over that, and we kind of have to stick with CT to some extent. Do you think that's fair, or do you see a way around it?
I think it is fair. I mean, certainly in Glasgow, our management are responsive. If you come up with really solid clinical data that you should be doing another imaging technique, they do respond to that. I mean, we changed our myeloma pathway pretty extensively in that now. That's probably smaller numbers, similar to mesothelioma, so I think there's a kind of precedent there. I think people are a little bit scared of doing pleural MR as well. It's quite a different technique, and people sometimes think it's something weird and wonderful, but actually the building blocks of it are really just the same as, liver MR or renal MR. The principles are very much the same. It's just kind of knowing your anatomy, knowing the kind of hints and tips. So whole body MR, I think, will come in gradually because it's got lots of applications. I think it'll just take time. Time and money.
If the increasing acknowledgement of early stage disease and that Simon described as becoming kind of, certainly the T1 is so common. I mean, I think Matt's data is nearly 50% of our cases are stage 1, not T1, but stage 1. You kind of need better tools, and MR is the obvious better tool.
Yeah, and the other point I make, and a similar chat he talks about myeloma, is that in actual fact, if you look at the investigation of prostate cancer, for example, they've moved pretty much to using MR for screening. And that's been done in an NHS setup with no more scanners, and we've just soaked up that pressure. So there are precedents there, that if something is better for the patients, then it will get done.
You've done much more MR with thorax than I have, and kind of following up on Kevin's point about should MR replace, if you like, CT in the early staging.
Yeah.
In your experience, so in all, the image quality you get out is very often dependent on the patient being able to lie still for a prolonged period of time, follow breathing instructions. Do do you have a notion of how many MRs we do for meso that don't give diagnostic information?
Interestingly, not really that many. You know, if you are quite robust in your protocol setup, you can reduce your breath holds quite a lot. I guess as well, compressed sensing, AI will reduce your scan time. Use those, keep your image quality the same, but reduce the amount of time you're scanning, so AI is going to be useful. I guess as well, by and large, we're scanning people perhaps once the physicians have optimised them, you know, pleural effusions have been drained, then you get them into the scanner. So that's probably where having just good relationships with your clinical team, I think, really helps.
Can I add a comment to that? So for my PhD, we scanned about 60 patients, and actually it was before we touched them, before we drained any fluid, and so often they had chest full of fluid. Breath hold was 16 to 18 seconds, depending on how big the thorax was. One patient who really didn't manage, he still had diagnostic images, largely because he had big tumour lumps. It was quite obvious. But all the other patients managed reasonably good pictures, where you might struggle a little bit with voluming with the breath hold, but from a diagnosis point of view, they all managed really well, actually.